Okay, so I think we will kind of get started with this session. So you can see the agenda kind of broadly broken down here. I want to start by just verbalizing some of the instructions that I've given in iLearn over the last couple of days with regard to the final that's going to be next week. We're going to take a look at some examples from chapters 12 and 13. We'll overview some of the material from chapters 8 to 11, just kind of looking at some of the key points that we've looked at, seen so far. And then I will kind of, in the remaining time, kind of open up the floor to welcome any questions that you might have. So as the session progresses, if you do have questions, please write them in the chat. I can see the chat and I will endeavor to respond to your questions as they come up. Of course, if there are kind of many and they get kind of lost to the scrolling chat window, then they might be ones that I come back to later. If there are any issues with hearing me or seeing what's going on the screen, also please let me know in the chat. I'm kind of just going to assume that everything is working and keep on going until I see some indication otherwise. So one thing I did want to mention before we talk about the final is iEval, the evaluation system. We are now at, I think, 79%, which is above the threshold that I offered for the bonus points. So everybody in the class will get some bonus points. So thank you very much for responding to the evaluation system. We do really appreciate the feedback, and it does help in building these courses. Of course, going forwards, there may be more of a shift to an online focus. So things are likely to change significantly regardless of the feedback. But I do appreciate your comments and your time that you spent in providing the evaluation. So in terms of the final next week, obviously things are going to be rather different than what we were expecting a few weeks ago. Hopefully you've all been able to read the posts on iLearn and have been able to digest the information. The discussion board on iLearn is open if you do have any questions. I've been going through and answering these as they come up. That's a good way of seeing if the question that you have has already been asked and answered. What I will say here is just kind of a brief summary of what will happen on Tuesday. So at 11:30 a.m., so this is when the final would have started, you will get a link appearing in the assignments tab in iLearn. This will link you to the exam version that you are meant to complete. So this is slightly different than what I indicated in one of the posts. So you're now randomly distributed an exam version rather than doing it alphabetically. So that's the only difference. You'll get a link in assignments. You'll click the link and then you can hit the button to start the test. At that point, you'll be able to click another link which will allow you to download a PDF of the actual exam. And then on the exam itself, you'll see questions and the answer choices exactly like you've received for the midterms. You will then work through that exam and you'll submit your responses to each question on iLearn. So what you can do is download the exam, work through it on paper or scratch paper or whatever, and then submit your answers through iLearn. So it doesn't require iLearn to function throughout the whole time. As long as iLearn functions for you to get access to the exam and for you to submit the responses, that's kind of the extent of functionality that we need. If there are technical difficulties, then I will make other options available for submitting your responses. And that will be clarified as Tuesday approaches. Do you expect the work? So in terms of my request that you keep all the scratch paper, this is really just to make sure that you've actually done the exam yourself. I don't want you to just take the answers from somebody else, submit them, and then get a score that you don't deserve. The idea is that if there are some obvious discrepancies, I would like to see some evidence that you've actually done the exam rather than just getting given the answers. So you'll only be asked to send that evidence in a direct email from me after the exam. So don't worry about sending anything through in anticipation. Just make sure you keep all of your scratch notes and your scratch paper from the exam, just in case I ask for it. So the iLearn test interface, and maybe after the session, I'll make kind of just an example of what it will look like, an example test. What will happen is you'll just see 50 questions. They'll be labeled question 1, question 2, question 3, and each question will have 5 options, A, B, C, D, and E. And so each question will then link to that relevant question on the PDF, and then you'll choose the option A, B, C, D, or E based on the correct answer or your perceived correct answer from solving the question from the PDF. I think even if it's not necessarily clear now, when you actually start it, it should be relatively obvious what you have to do. Still confusing how we also... yes, the free response extra credit is still a thing. So you will type your responses in a text box within iLearn. So the format of the exam is exactly the same as what I was planning for in paper. Yes, and you won't necessarily have 3 hours, but you will have until 2:30 p.m. So assuming you start at 11:30, you will have 3 hours. If you're late starting, then you will have less time. Okay, so if you have any further questions at this point, just because I don't want this session to just be on the final, if you do have any further questions, please post it in the discussion section on iLearn. I'll go through and respond to these as queries come up. Okay, so that's going to be the final. Hopefully things will go smoothly, and we will kind of grade everything as we would do a sit-down final. I do anticipate that the overall average will be higher because it's open book. That's fine. I'm not changing grade boundaries or anything. It just means that we'll have a higher pass rate or a higher rate of strong scores in this class. That's not a problem. So you're not going to be penalized in any way for the change in the format. It will only advantage you, in my opinion. This ID, you mean? This is the ID for Zoom. Someone was asking about this earlier. You can also access this from this link that is now posted in the chat. So I'm not answering questions about grade boundaries. The grade boundaries set out in the syllabus are going to stand. So the cutoff for an A is 800. I'm not yet communicating whether that's an A or an A minus. What I do want to say is that the C minus cutoff is 55%. So 550 points to get a C minus. That is a guaranteed cutoff. So just bear that in mind. Okay, so I want to move on now and focus on some examples from the material in chapters 12 and 13. So these are going to form a slightly stronger portion of the final than kind of the other parts of the course, simply because we do have 20 questions devoted to chapter 12 and 13. So this will be an opportunity to go over some of this material and hopefully reinforce some of the concepts and the application of those concepts, which is what you'll be mainly tested on in Tuesday's final. So this document, or a document that goes along with this session, was uploaded to iLearn. If you want to download a PDF of the questions that we're going to run through as examples, it will look a little bit different just because I've spaced things out on my version to give space for actual annotation. So if you haven't got access to this PDF and you want it, it's uploaded to iLearn, and I think it's linked through the most recent announcement. Okay, so the first example that we're going to look at is asking us about the vaporization of ammonia. So we're given information relating to the enthalpy and the entropy of vaporization at its boiling point. So we're given the information relevant for the vaporization of ammonia at its boiling temperature. We're then asked to determine what the entropy change of the whole universe is when 1 mole of our liquid ammonia vaporizes in a room which is at a temperature of 34 degrees Celsius. And we're assuming that the final temperature of our gas is minus 33.34. That's essentially irrelevant. I think that may actually be a mistake in the question. But we're going to address this question, and we're going to kind of look at some of the background behind how we go about solving this question. So the first point to note is that we're told that we're dealing with the normal boiling point. What that means is, well, at the boiling point, we have an equilibrium. So the boiling point will have an equilibrium between the liquid and the gas. So we know at equilibrium, we essentially have a process which is not spontaneous in either the forward direction or the reverse direction. So in that sense, our delta G is going to be equal to 0, and the overall entropy change of the universe is also going to be 0. This is for this boiling occurring at the boiling point. So we need to specify that these are true at the boiling point. In the question, though, we're asked to consider what happens at 34 degrees. Now, 34 degrees Celsius is clearly above the boiling temperature. The boiling temperature is minus 33 degrees Celsius. And when we're above that boiling point, what this tells us is that we're going to have a vaporization event occurring which will be spontaneous. So above the boiling temperature, the spontaneous transformation is for the liquid to boil. So vaporization is spontaneous. And when we have something which is occurring spontaneously, what that tells us is that delta S universe must be greater than 0, and our Gibbs energy change must be less than 0. So there are a couple of methods of actually going about solving this question. And if you do have questions as we're going through this, please note them in the chat. I will try to address them and clarify any points that are not making sense. But we're going to go through 2 methods to determine what the entropy change of the universe is in this particular scenario. So the first method is going to consider the entropy change in both the system and the surroundings. And this comes directly from the first law, from the second law of thermodynamics. The second law of thermodynamics tells us that in a spontaneous process, the entropy of the universe must increase. And from that, we can derive the fact that the entropy change of the universe is equal to the entropy change in our system plus the entropy change in the surroundings. So we have to consider the entropy change in both of these parts of our universe in order to determine what the overall entropy change is. So let's consider what information we actually have. Delta S system, this is the entropy change associated with vaporization, and we're given that in the question. So we're given the entropy of vaporization. That is the 97.4 joules per mole Kelvin. And we have to determine what our entropy change in the surroundings is. If we want to determine the entropy change in our surroundings, we have to recall the relationship between heat and entropy. So we encountered this relationship that delta S could be written as the reversible heat divided by the temperature. So what this means is that if the process is occurring reversibly, then the entropy change associated with it can be determined by the amount of heat that is transferred during that process divided by the temperature of that process. When we apply this to the surroundings, what we arrive at is that the entropy change in the surroundings will be equal to the amount of heat that is flowing either into or out of the surroundings due to whatever process is occurring, divided by the temperature of the surroundings. So we can write that as Q surroundings divided by T surroundings. The energy flowing into our surroundings or coming from our surroundings is due to the process that's occurring in the system, which is this entropy, which is this vaporization process. So this amount of heat that is coming from the surroundings is equal to the minus, or is equal to minus the enthalpy change of the system. And we have the temperature still of the surroundings. So we have this minus sign here because delta H is referring to the enthalpy change in the system. The surroundings is essentially seeing the opposite of that because the surroundings is either receiving that energy, and so it would have the opposite sign. So we have delta H system from our question, and we know the temperature of surroundings from the question. So we can plug some of the numbers in now in order to actually determine the entropy change of the universe. So let's just write this out in full. Delta S universe, based on this substitution, is going to be equal to minus delta H system divided by T surroundings plus delta S system. So we have minus the enthalpy change. We're going to convert to joules per mole. So we have 23.35 times 10 to the 3 joules per mole divided by the temperature. The temperature is the temperature of the surroundings, so 34 degrees Celsius, but we want to convert that to Kelvin. And then the entropy of our system is the entropy change associated with vaporization in the system, which is 97.4 joules per mole Kelvin. So when we sum all of these factors together, we get a value of positive 21.4 joules per mole, joules per mole Kelvin. We can think about whether or not that makes sense. So we're expecting an entropy change of the universe to be positive because this liquid is boiling above its boiling temperature. And that's indeed what we calculate. We calculate a positive delta S universe value here, which is consistent with this being a spontaneous process. So this is the first method where we've essentially evaluated all of the components of the entropy separately. We've considered the entropy change in our system, and we've considered the entropy change in our surroundings, and we just summed these together to give this entropy change of the universe. Now, we also introduced a concept in class, the Gibbs energy. And the Gibbs energy tells us whether or not a process is going to be spontaneous. And the great thing about the Gibbs energy is that it actually considers both what's going on in the surroundings and the system in terms of the entropy together. So we can determine whether a process is spontaneous based solely on knowing what's going on in our system. And so we derived this expression, or we wrote down this expression, that delta G, which is the change in our Gibbs energy, is delta H minus T delta S. The criteria for a process to be spontaneous is that delta G must be less than 0. And we actually define delta G in terms of the entropy change of the universe. So we actually said that the change in the Gibbs energy is defined as being minus T delta S universe. So based on how delta G and delta S universe are actually related, if we calculate delta G for this vaporization process, we can very straightforwardly determine delta S by dividing by the temperature. So let's calculate delta G for this vaporization process. So we have delta G is delta H minus T delta S. Our delta H is 23.35 kilojoules per mole. And then we're subtracting T in Kelvin, which is 34 plus 273, multiplied by delta S, which we're going to convert to kilojoules simply because we have kilojoules in our delta H here. So we have to divide the entropy by 1000, which gives us 0.0974 joules per mole Kelvin. Sorry, kilojoules per mole Kelvin. We can determine the value of delta G, and we come up with a number which is minus 6.57 kilojoules per mole. And again, this makes sense. We know this process is going to be spontaneous. And so this negative value of delta G is what we would expect based on that being spontaneous. So now we can essentially rearrange this expression to say that delta S universe is equal to minus delta G divided by the temperature, which is 6.57 times 10 to the 3 joules per mole, divided by the temperature, 34 plus 273. And that gives us the answer that we had before, 21.4 joules per Kelvin per mole. So these two methods to get to this answer are essentially equivalent. What we did initially was focus solely on the entropy, and we summed the entropy in each case in both the system and the surroundings. In the second case, we used this definition of Gibbs energy to determine the change in Gibbs energy, which tells us whether something is going to be spontaneous or not. And that Gibbs energy change is related to the entropy change of the universe via this expression. So either method will give us the same answer. They are essentially entirely equivalent. It's just delta S universe is wrapped up within this value of delta G. So yeah, I think these questions are posted on iLearn in response to that question. Let me just double check that so I'm not giving you any false information. I may have been lying to you. Has anybody found the PDF on iLearn, or is it actually not there? Okay, I will upload this now. Hopefully you can see that almost right away. Okay, so that this PDF is now uploaded to the course material section. I apologize for not having done that. I thought I had, but apparently I had not. So one of the questions is, how do we know delta G is T delta S universe or minus T delta S universe? And this is basically a definition. Delta G is a construct that we formulate based on kind of our understanding of what defines a spontaneous process. And by defining it in this way, what it allows us to do is determine what this Gibbs energy change is in a system or in a process, given knowledge of only what's going on in the system. So what that does is it gives us this nice value that we can kind of assign to a process that then tells us something about the spontaneity of that process. So put very simply, this is by definition. Delta G is equal to minus T delta S universe by definition, because it gives delta G the properties that allow us to use it to assess spontaneity. Okay, so let's move on now, because I don't want to spend all of this time looking at delta G. I know several of you did express through office hours that this question and several questions in the practice were kind of stumping you a little bit, so hopefully this clarifies exactly what the procedure is. So let's move on to another example. We're not going to spend much time on this example because it's very similar to the first one. What we're told in this question is that we have this decomposition of dinitrogen tetroxide to nitrogen dioxide, and we're given delta H and delta S for this decomposition process. And what we're asked to do is determine at what temperature this process is at equilibrium. So based on what we spoke about in relation to the previous example and what we know about delta G, at equilibrium, we have a value of delta G which is equal to 0. That means that when we look at our expression for delta G, which is delta H minus T delta S, we can set delta G equal to 0, rearrange it to get delta H is equal to T delta S when we're at equilibrium. So in this case, we would substitute in our value of delta H and our value of delta S, and this will allow us to solve for this equilibrium temperature. And this is true for any process at equilibrium. If we know delta H and delta S, we can determine the temperature at which that equilibrium will occur. So that's one way we can actually calculate what the melting temperature of ice might be if we know the enthalpy and the entropy change of the ice transformation. And that's something that we actually did in class. So if you don't remember how to do that, look back in the notes. That's something that we did do in class. So I want to move on now to a few examples from chapter 13. Chapter 13 is clearly something that has struggled in these last few days with cancelled classes. I have uploaded videos. Hopefully, as many of you have watched those videos. Those videos are covering, just kind of going through the notes, very similar style to in the in-person lecture, but also you can watch those from the comfort of your own home. If you opt not to watch them, I would recommend that you do watch them, but if you don't, then just make sure you work through some examples, because the concepts that we're dealing with in chapter 13 are a little bit harder to grasp unless you've seen it several times. So hopefully the examples that we're going to go through now will clarify any problems or questions that you might have. Again, please ask any questions as we go through this example. So in this particular example, we're considering this reaction between these kind of model molecules. So A, B, C, and D are just representing some arbitrary molecules. We're given the stoichiometry of each compound. And what we're asked to do is determine which of these reaction rates is false, which of these expressions for the reaction rate is incorrect. So we have to remember a couple of things relating to reaction rates. Firstly, when we define a reaction rate, what we're looking for is a positive number. So our reaction rate should be a positive number. Secondly, we want the value of our reaction rate to be the same however we formulate it. So we can define the speed of this process based off of the rate of change of any of these species, A, B, C, or D. But we want to make sure that the reaction rate that we actually specify is always the same, whichever one of these compounds we actually use to define our rate. So another thing that we have to remember is that the reaction rate has the same value for whichever species it's defined by. So in order to formulate what the reaction rate of this expression should look like, we should cast our minds back to the general reaction rate that we can use and apply in this case. So we can formulate the general reaction rate expression by taking 1 over the stoichiometry. And we're going to say that we're referring to compound X. Compound X can be any arbitrary compound in our reaction. V sub X is the stoichiometric number of that particular compound in our expression. And then we multiply by the rate of change of concentration of that compound. So we're defining the reaction rate as 1 over the stoichiometry multiplied by the rate of change of concentration with respect to time. One thing we have to remember, firstly, this is the stoichiometry number. We have to remember that in order for a reaction rate to always be positive, we actually have to change the sign of this expression to match whether or not we're dealing with products or reactants. So if we're dealing with reactants, we have to put a negative sign. And if we're dealing with products, then we have a positive sign. The reason that we do that is because if we're dealing with a reactant and its rate of change of concentration is negative, because a reactant is consumed in a reaction, its concentration is decreasing, then this delta concentration by delta T will be negative. So we add another negative into this expression in order to make this overall rate that we're determining a positive number. So you just have to remember that if we're dealing with a reactant, we need to put a negative sign in there. And if it's a product, we just have a positive sign. So using this general expression, we can actually now write down four relationships that define the rate of this reaction. So we're going to write down that the rate is equal to, firstly, we'll start by defining our rate through species A. So we have a stoichiometry number of 3. So we have 1 over 3. And this is a reactant, so we need to make sure we put a negative sign in there. And then we're just multiplying that by the change in the concentration of A over time. So that is one way of formulating our rate. This must be equal to the equivalent way of formulating the rate based off of any other species present in this reaction. So for B, we would have minus 1 over 5 delta B, delta concentration of B by delta T. And again, that is going to be equal to the same formulation for C and D. For C and D, we're dealing with products, so we don't need to have the negative sign present. So for C, we have 1 over 2 delta C by delta T. And then for D, we have 1 over 4 delta concentration of D by delta T. So all of these formulations are equal. They're all defining the rate of this reaction. And because we've normalized everything by the stoichiometry and we've added the sign for whether it's a reactant or a product, we will get the same number for the rate using any of these expressions. What we're actually asked to do in this question is just identify which of the relationships of these answer choices is incorrect. So which of these does not result from rearranging any two of these expressions in some mathematically consistent manner. So if we look at the A and B relationship, what was shown in option A is rearrangement of this expression, where we've multiplied by minus 3 to get rid of the fraction from the left-hand side. And so that gives us a 3 over 5 on the right-hand side, which is exactly what we're given in the answer choice. So we can go through all of these options and assess whether or not that's what we would obtain when we rearrange this rate law. And what we find is actually that it's expression E that is incorrect. What we should have in this expression is a negative sign in front of our 3/4 on the right-hand side. So this is incorrect because there was no negative sign present. We're missing our minus. All these other ones are consistent with rearranging this expression, and so they're all relevant ways of expressing the rate. Okay, let's move on to the next example, which is also moving on with kind of going in the order that we encountered this material in class. This next example is giving us some information on the rates of this particular reaction as certain conditions in that reaction are varied. So we're asked to determine the overall order of this reaction given this information where we have multiple experiments performed at different concentrations of the reactants. Now in class, and in I think one of the example videos that I uploaded, we were dealing with molar units. In this case, we're dealing with a gas phase reaction, and so we're actually reporting the concentration as a pressure. Pressure is an appropriate way of expressing concentration if we're dealing with a gas. And so all of the times that you see torr in this question, you could similarly replace with molarity for something which is occurring in a solution. So torr here is just reflective of the concentration of that particular species. So the strategy to determine the reaction order is to compare pairs of experiments and see what happens when we change the concentration of one species at a time. So the order of the reaction tells us how much the reaction rate varies when we change the concentration. So if we have a first order reaction, what that means is that if we double the concentration, we'll double the reaction rate. If it's second order and we double the concentration, we would get 4 times the reaction rate. So based off of the information that we're given in terms of the changes in concentration, we can determine what the order of this reaction is with respect to each individual reactant. And then the overall order is just the sum of those individual orders. So we'll go through this fairly quickly because I have uploaded another video on this process. So the rate law has similar form to, right, like yes, so that's exactly what we're about to write down now. So we can write down a very general rate law for this process and for any process. And we can write down that the rate is equal to a rate constant K multiplied by the concentration in this particular example of hydrogen raised to the power of some order multiplied by the other reactant ICl raised to the power of that order. So this is another way of expressing the rate. So in this case, we're using our rate constant. And we have M and N are the reaction orders with respect to each of these particular reactants. So there are several unknowns in this. We don't know our rate constant and we don't know what the reaction orders are. Now, the way the rate constant is defined is it doesn't vary with concentration. So the rate constant is true for a particular reaction, regardless of the relative concentrations of the species in that reaction. What that means is that in experiments 1, 2, and 3, we have the same value of K. The reaction orders are also going to be the same regardless of the concentrations. So what we have are 3 unknowns, but 3 pieces of information that allow us to elucidate the values of each of these unknowns. The procedure for doing this that we've adopted in this class is to take pairs of experiments and compare them. And we're comparing the experiments where we're only changing the concentration of one of the reactants. So if we look at experiment 1 and 2, we're keeping the concentration of H2 the same, but we're varying the concentration of ICl. So if we write down the rate of equation 1 divided by the rate of equation 2, because K doesn't vary with concentration, we'll actually have K in both the numerator and the denominator, so we would cancel those away. We'd have H2 raised to the power of M, but we're keeping the H2 concentration the same, and so we can also cancel that factor out. So all we're left with is the other species, ICl, in reaction 1, raised to the power of N, divided by ICl in reaction 2, raised to the power of N. So now we've gone from something where we have 3 unknowns to something where we only have 1 unknown. So now we need to do some mathematical manipulations. We can get rid of our N in the power of our concentration by taking a logarithm of both sides. And that allows us to rearrange this expression into the form where we have N is equal to the log of rate 1 divided by rate 2 divided by the log of the concentration of ICL in experiment 1 divided by ICL in experiment 2. All of the information in this fraction is available from our table of data, and so we can start plugging some numbers in. We're taking the log of 1.34 divided by 0.266, and we're dividing all that by the log of 250 divided by 50. Turns out that both of these fractions are equivalent, and so when we calculate this value, we find that we get 1.0 for the reaction order of ICL. So we get n is equal to 1.0. We can adopt the exact same procedure for, isn't 250 the value for H2? Yes, you are right. I got ahead of myself. We should have 325 divided by 81. Thank you for catching that. So that is the concentration of ICL between experiments 1 and 2. And so we get an answer of 1 for the order of H2. We can adopt the exact same procedure to determine the order of H2. And in that case, we need to pick the pair of reactions, the pair of experiments, where the concentration of H2 is changing, but the concentration of ICL is staying the same. So we have experiments 1 and 3 will conform to that configuration. And yes, indeed, thank you in the chat for pointing out another mistake. This should be 0.331. The answer is the same, but some of the numbers were different. So this is correct for the moment. Thank you for pointing that out. When we compare experiments 1 and 3, we are essentially able to arrive at a similar expression, but in this case, we're going to have the concentration of H2 raised to the power of m in experiment 1 divided by H2 in experiment 3 raised to the power of m. We can rearrange this in exactly the same way. We'll get something that looks very much like this expression with the relevant changes to reflect the hydrogen concentration. And so when we plug the numbers in from our table of data and we do it correctly, we'll also find that the reaction order is 1.0 for hydrogen. So that means that our total reaction order, the overall order, is equal to 2. It's the sum of m and n. So in this case, we can identify that B is the correct answer. For the purposes of this example, we're going to go one step further, and we're going to determine the value of the rate constant as well. So now that we have both m and n, we're down to just having one unknown. So we can use any one of these experiments. In fact, we could use all of the experiments, we should get the same number, but we can use any one of these experiments to solve for k to determine the value of our rate constant. So let's choose experiment 1. In experiment 1, we had a rate of 1.34, and the units are torr per second. So you can just think about this as a concentration per second. That's equal to K multiplied by the concentration of H2, which is 250 torr, multiplied by the concentration of ICL, which is 325 torr. So we can rearrange this expression and solve for K, and we find that it's 1.65 times 10 to the minus 5. And we need to work out what units we're dealing with here. So when we have essentially torr squared on the right-hand side, and we're dividing throughout by torr squared, then we get 1 torr on the denominator. So we get torr to the -1 on the left-hand side. So our units are torr to the -1, seconds to the -1. And this is consistent with what we would expect the units of our second order reaction to be. It's a per concentration per time unit. So in class, we wrote down that for a second order reaction, we'd have per mole per second. Here we're replacing our per molar with torr. If we had a first order process, then the units of K would just be in seconds to the -1. For second order, it's a concentration unit, or per concentration unit per second. For third order, you could similarly determine what that would be. It would be a per concentration squared per second. And you can also have more exotic units if you have an order of reaction which is 1.5 or 2.5. Is that K the same? So this K is the rate constant, regardless of the fact that we're referring to the concentration in units of pressure. It's still a rate constant. It's still the value of K in our rate law. Okay, let's move on now to something that we didn't really focus much on in class or even in the videos that followed the class, but this will give us an opportunity to think about it a little bit more. So in this question, we're given various reaction energy profiles, and we're asked to determine which of these reactions requires the most energetic collisions to reach the transition state. So in answer to this question on the rate constant, so the rate constant is dependent on temperature, but it's also dependent on things like the orientation of the reaction. So for a particular reaction, and you have a value of K, then it's the temperature which will be the thing that varies K. But for some arbitrary reaction, the value of K will depend on temperature and the actual geometry of the reactants and how they actually come together. So that's something that we'll get onto in the next example, where we actually look at how K varies with things like temperature. Okay, so these 4 plots show different reaction pathways. So the way that we interpret these is that we're starting with our reactants with some energy, and we end up with some products at a certain energy. So if we have an exothermic process and our products are at lower energy, then we would draw them lower in this diagram. But we connect our reactants and products not with just a straight line, but we have this kind of hump in the energy profile. And this hump reflects this activation barrier, this minimum energy that we need our reactants to have in order for the reaction to occur. So if we just consider this in terms of 2 particles coming together, they will be traveling with some speed, and that speed is going to be dependent on temperature. When they have a certain speed, they have a certain kinetic energy, and so the energy associated with this collision is going to depend on the temperature. If the energy associated with the collision is bigger than this barrier to the reaction occurring, then the reaction should happen. We'll form the transition state, and that transition state can then go on to form our products. So the transition state is the peak of our transition state is essentially the peak of our reaction energy diagram. So in these four examples, the peak of our energy profile represents the transition state. So the activation energy is then defined as the height of the barrier that our reactants have to surpass in order for the reaction to happen. So we define our activation energy with the symbol E subscript A, and this is the minimum energy of the collision to allow the reaction to happen. Now, energy is not the only factor. If the molecules react in the wrong orientation, then even if they have enough energy, they may not go on to react. So there are more things at play than just the concentration, just the temperature. But for the moment, we're just focusing on the role temperature plays. So the activation energy is essentially the difference in energy between the reactants and the transition state. So in these figures, it's the height of this barrier as indicated. So then quite simply, the reaction which requires the most energy to reach the transition state is going to be the reaction that has the biggest energy barrier. And so clearly it's B that has the biggest energy barrier. The height of, or the difference in energy between the reactants and the transition state is the largest. So we would say that B has requires the most energetic collisions. So these diagrams are all showing different kinds of reactions. So in reaction A, we're dealing with something which is exothermic. So when this reaction happens, we're releasing energy. And as a result of releasing that energy, our products are going to be at a lower energy than what our reactant started at. So an exothermic process is characterized by the products being at lower energy than the reactants. For reaction B, we're actually dealing with an endothermic reaction. And an endothermic process, the reactants are pulling in energy from the surroundings, and so the products actually end up with more energy than the reactants. So the question is, do we need to know about the state from the peak to the product, or is that not really important? It depends on the reaction profile itself. So we cut short chapter 13 somewhat in that we're really focusing only on single-step reactions, and a single-step reaction will just go from A to B with one transition state. There are situations which we're not going to get into in this course, but where you have multiple transition states and multiple activation energies. And then we do need to know a little bit more about what's going on in the reaction in order to identify things like the rate determining steps. But that's not something that we're going to cover in any detail in this course. You're welcome. I just need to plug in some power. Okay, so all of these are referring to either exothermic or exothermic reactions. The height of the activation barrier doesn't really, is not really impacted by whether the reaction is endothermic or exothermic. You can have a very large activation barrier to an exothermic process, or a very small activation energy for an endothermic process. There's really no correlation there. For a combustion reaction, for example, we know things are not always spontaneously catching fire. We do have to put some energy in for the combustion reaction to occur and to then continue spontaneously. It's this activation energy that is what we have to supply in order for the reaction to initiate. So when we generate a spark, we are providing this activation energy, and then when the combustion reaction happens itself, the products are very low in energy. It's a very exothermic process, and it becomes self-sustaining. The energy that's produced as our reactant is converting to products is increasing the temperature, and it's allowing all of the other molecules to get over this activation barrier. So a combustion reaction is an example of a self-sustaining reaction, and it's because it's actually generating the energy it needs to get over the activation barrier. Okay, so the final example that I want to go through from chapter 13 is going to relate this activation energy to the actual reaction rate. So the bigger the activation barrier, the bigger the activation energy, the slower the reaction will go. The reason for that is that fewer molecules will have the energy that they need when they collide for the reaction to happen. So as the activation energy increases, we would expect the reaction rate to decrease. And it turns out that we can relate the rate constant for a reaction to the activation energy and one other factor. So we'll talk about this through this example. This other factor is something related to the frequency of collisions and the geometry that those collisions have to adopt. So we're talking about the Arrhenius relationship. The Arrhenius relationship relates our rate constant K to a frequency factor A multiplied by the exponential of minus our activation energy divided by our T. So we have our activation energy we have this frequency factor, and this frequency factor depends on the collision rate between our molecules, and it depends on the geometry of that collision. So if a reaction will only occur with a very, very precise geometry of the collision, then it means fewer collisions will actually result in a reaction. And so we get a frequency factor which is smaller as a result. So if we get fewer collisions or fewer collisions that can actually result in a reaction, then we'd find this A factor gets very small. The activation energy is what we've just been talking about. It's the energy that the collision requires in order for the reaction to occur. And these two things combine to actually determine the value of our rate constant. So we have in this expression two unknowns. In this reaction, in this question, we're measuring this decomposition reaction, and we're measuring the reaction rate constant as a function of temperature. So we're doing two experiments, or we're measuring the reaction rate at 486 Celsius and 563 Celsius. So we have this expression in the Arrhenius relationship, but we want to get rid of one of the unknowns. We're asked to determine the activation energy, which is in our exponential, but we don't know anything about the frequency factor. So the way to address this is to use a slightly different form of the Arrhenius relationship. And this relationship, or this new form of the relationship, looks very much like the Clausius-Clapeyron equation. So we're going to write down a different form. And the different form of it takes the look of the logarithm of K1 divided by K2, and that's equal to minus the activation energy over R multiplied by 1 over T2 minus 1 over T1. So this comes about from substituting K1 and T1 and K2 and T2 into this expression, and then dividing them. So similar to what we did with the rate laws, when we look at two different temperatures, we're not changing the value of either the activation energy or the frequency factor. So when we divide the two together, we can actually start cancelling out some of the things that are not changing. So in this case, what we've done is cancel out the frequency factor. And so that gives us an expression that allows us to determine the activation energy based on information from two different reactions at two different temperatures. So we just now have to substitute our information into this expression. So we can take the logarithm of 0.0214, which is the reaction rate from reaction number 2, divide it by 0.00105, which is the reaction rate from 1. And that's equal to minus the activation energy divided by R, which is 8.3145, multiplied by 1 over the temperature for what's on the denominator. So the 0.00105 is going to coincide with the 486 degrees Celsius. So we have 486 plus 273, so we want it to be in Kelvin, minus 1 over 563 plus 273. So we can plug these numbers in and solve for our activation energy. And we get a value of 206,549 joules per mole. But we would express that in kilojoules per mole. So that would be 206.55 kilojoules per mole. And then if we compare it to the answer choices, clearly then we're matching up with E. So the Arrhenius relationship allows us to derive some values for the activation energy or the frequency factor, if we so chose, based off of measurements of the change in the reaction rate constant with temperature. So it is very similar in principle to the Clausius-Clapeyron equation, and this expression actually looks very much like the Clausius-Clapeyron equation, whereas that was allowing us to determine different vapor pressures at different temperatures. This is allowing us to determine different rate constants at different temperatures. Okay, so, well, I would like to ask now, before we kind of just do a little bit of a review of the other parts of the course, are there any questions on what we've done so far? Any questions on chapter 12 or chapter 13 material? If you do have any questions, please put it into the chat. I'll try to answer those questions before we move on. How does S surroundings relate to Q reversible? So this is, let's go back to where we introduced that. So this definition of the entropy, this applies for the process that's occurring in our system. So when our process occurs reversibly, then what we have is the amount of heat that flows in that process is the reversible heat. So when it's at equilibrium, we have the reversible heat. So this is how we define delta S in our system. But what we can also do is say that when we're considering the surroundings, the entropy in our surroundings will change based on however much energy it receives. It doesn't make any sense to talk about reversible heat transfer in terms of the surroundings. And so the entropy change in our surroundings is equal to just whatever the amount of heat that's either going into or out of the surroundings So if we're dumping 100 kilojoules into our surroundings, then we could determine delta S of the surroundings based just on that amount of energy. It's kind of not relevant to refer to reversible or irreversible from the point of view of the surroundings. Does that make any sense? Awesome. So is the frequency factor a constant? Does it vary at different reaction conditions? Yes, it could do. So it would vary at different pressures because the pressure defines the rate of collisions. So if you were to do this reaction at a different pressure, you might find that your frequency factor does change. So it's not always a constant of a reaction, but it is a constant as a function of temperature. So if we're just varying temperature, we would expect the frequency factor to stay the same to a first approximation. Can you please give an example of when we have a reaction first order compared to one of third order based on the info we're given without it being told explicitly? So you wouldn't, the most likely situation that you would find yourself in if you're presented some information on a reaction and you're not told explicitly if it's first order or second order. One kind of situation would be when you're asked to determine what the order is. The second situation would be you might be given a rate constant, and from the rate constant, you should be able to identify the reaction order. So based off of what we were writing down here, for example, if your rate constant has units of just per second, then that immediately tells you that we're dealing with a first order process. If it's in per concentration per second, so that could be m to the -1 per second or tau to the -1 per second, then that would indicate second order. If it was m to the -2 per second or tau to the -2 per second, then that would indicate third order. So the main way that you would tell is from the units of the rate constant, if you're not given that information explicitly. Yeah, I'm going to very quickly, I'm probably going to end this session at 5 p.m. So we're going to spend the next sort of 10 minutes just very, very quickly writing down some key bits of information from chapters 8 through 11. And then I'll give you 5 minutes or so to ask any additional questions that pop up over the next 10 minutes or so. So the first thing that we're going to very quickly talk about are oxidation numbers. When you're determining what the oxidation number is of an atom, then it's very important that you know what the oxidation numbers of the atoms that are of the other atoms in your molecule. So the way that we do this is by identifying that there are many atoms that when they're in a molecule will have a fixed oxidation number. So one of those is oxygen. Oxygen, when it's in a compound, will almost always have an oxidation number of -2. Hydrogen would be +1. Fluorine, or any halogen, for example, or most halogens would be -1. And there's a few of these that are always fixed. If we're dealing with an atom in its pure elemental form, so oxygen molecule O2, for example, then the oxidation state is 0. Or the oxidation number is equal to 0. For any atom in its pure element, the oxidation number is 0. If we're dealing with an ion, then the oxidation number is equal to the charge on the ion. If we're dealing with a neutral compound, then we have the oxidation number of a neutral compound. This would be the overall oxidation number, would be 0 if it's neutral. If it's a polyatomic ion, so sulfate, for example, SO4 2-, then the oxidation number is equal to whatever the charge is on that polyatomic ion. So in the same way as our atomic ion, we apply the same rule for our polyatomic ion. So you should be familiar and comfortable with being able to assign oxidation numbers of atoms that have variable oxidation states. So things like iodine, things like sulfur. These are pretty typical examples that you might come across where the atoms have oxidation states that vary depending on what kind of molecule they're present in. So something which is perhaps one of the more fundamental things that I hope you can take home from this class, and that is the laws of thermodynamics. So we encountered several laws of thermodynamics. So we're just going to quickly recap these now. The first law of thermodynamics, this is the statement of energy conservation. So it tells us that energy can't be created or destroyed. That is to say that the total energy of the universe is constant. It doesn't increase or decrease, it's at a fixed amount of energy. So if we have an isolated system, so an isolated system is one in which we don't let any matter or any energy flow, then this will have constant energy. And so you can actually consider the universe as being an isolated system from this point of view. And we mathematically derived or defined the change in the internal energy of a system that is interacting with its surroundings must come about due to either energy flowing as heat or work being done. So we say that delta E, which is the change in the internal energy, is equal to the amount of energy that transfers as heat plus the amount of energy that transfers through work. Heat being the transfer of energy across a temperature gradient, and work being the concerted motion or the energy exerted due to a force acting over some distance. So if you're pushing something or if you're expanding, then you're doing work because this force to cause that change is acting over some distance in space. So that is how we define work. The second law moves on a little bit. So the first law tells us that there are essentially some hard and fast rules to decide whether or not a process is allowed. And if it breaks the first law of thermodynamics, it's not allowed. So any process that consumes energy, or any process that generates energy for free, is prohibited by the first law of thermodynamics. That's not actually to say that it doesn't. So the first law will allow certain things to happen that are also prohibited, but they're prohibited by the second law. So the second law of thermodynamics relates to entropy. And this is this idea that one can measure disorder. One can assign a numerical value to the amount of disorder or dispersion of a system. And the second law tells us the entropy of the universe must increase in a spontaneous process. So what's that saying is If we have a process that occurs spontaneously, then it means that the entropy of the universe must be increasing. So delta S universe must be getting larger. If we're dealing with a process which is occurring at equilibrium, then our delta S universe is equal to 0. And that's by definition for a process at equilibrium. The third law of thermodynamics. This allows us to define the entropy scale. It defines the 0 entropy state. And it defines the 0 entropy state as 0 for a perfect crystal. So the entropy of a perfect crystal at 0 degrees Kelvin, so absolute 0 temperature, is 0. So that it has 0 entropy. We didn't explicitly talk about it, but there is also a 0th law. And the 0th law is what allows thermometry to work. What the 0th law tells us is that if we have system A in thermal equilibrium with system B, and then we add something to the system, add something to this network, which is in thermal equilibrium with B. So we add in C, which is in thermal equilibrium with B. What the 0th law tells us is that this will also, by definition, mean that A and C are also in thermal equilibrium. So this is the principle on which thermometers work. When you bring a thermometer into a system, we're assuming that it reaches thermal equilibrium with that system. The 0th law of thermodynamics is kind of an official statement of this observation, this experience. So we are basically out of time. I don't want to run past 5 because I know people will have other classes and stuff that they need to get to. But in these last few minutes, if there are any questions, please do ask them. Is it okay if you address a homework? If you have any homework issues, please email me. It's easy to address those on an individual basis rather than through this, this chat. So the last few things that we're not going to go over, but I do suggest that you spend some time looking at is the idea of the ideal gas, how we can define an ideal gas, what makes an ideal gas different from a real gas. I would also suggest that you spend some time reviewing calorimetry, getting a better understanding of how a calorimeter works, how you use data that you would collect in a calorimeter in order to determine the enthalpy change of a process. As hopefully many of you now know, Born-Haber cycles were used to determine lattice energies of salts. This is something that came up in chapter 9 and was featured on the midterm. I do suggest that you spend a bit of time to refresh your memory of Born-Haber cycles and how one constructs a Born-Haber cycle and actually uses the information to determine the lattice energy. And finally, I would suggest that you have to, that you should review some of the concepts surrounding vapor pressure. So vapor pressure describes the partial pressure of a molecules from a liquid in equilibrium with the gas phase. So we looked at things like Raoult's law to relate the mole fraction and the partial pressure to the saturation vapor pressure. So this is something I would suggest looking up on as well. What types of problems do we have to pay attention to stoichiometry? So stoichiometry, it's a very difficult question to answer. If you're, thermochemistry, for example, there would be a lot of cases where you have to remember the stoichiometry. Certainly in terms of any reactions where you have to count number of moles or have to compare the number of moles to reactants and products, stoichiometry is important. Reaction rates, as we covered today, you need to remember to consider stoichiometry. Anytime you're dealing with a reaction, you have to make sure that your stoichiometry is correct, because any theories that you apply based on the ratios of species in that reaction depend on you having the correct stoichiometry. Okay, well, I think we will wrap things up there. It doesn't seem like there are any additional questions coming. If you do have questions about the format of the final, please do post them on the forum, on the discussion session of iLearn. I will try to answer any additional questions there. And at some point, either today or tomorrow, this video will go up, assuming that Zoom has actually recorded it correctly. So this does conclude the content for the course. So hopefully things will go smoothly with online finals for everybody next week. As I said, there are going to be some contingency plans if things kind of don't work with iLearn. I will let you know of those as time goes on. Yes, we did surpass the IEVAL response rate, so everybody will be getting some bonus points. If you can post an example of the online exam. Yeah, so I will do that. So what I will do is essentially just post basically a blank test that will be pretty much exactly what the final should look like, assuming iLearn works. So that'll just give you a little bit of, it'll tell you what to expect essentially in the actual final. Yeah, so with that, I hope you all have a great finals week, and it's been a pleasure teaching you all. I've enjoyed teaching this class this quarter, and I wish you all the best.